Good afternoon, Professor. We are Team DFT team. And 下一页. We want to through the process using the extending D algorithm using 5 value to work in this circuit. In our case, the target for is A stuck at 1, shown in the diagram. Create a copy of a combinational logic, set its time frame 0. This is a crucial step because sequential circuit contain flip-flop, which makes testing difficult. To solve this, we separate the flip-flop from the circuit, treating them as connection between time frames. Effectively, we transform the sequential circuit into multiple copies of purely combinational logic. We start by focusing on the current copy, which we call time frame 0. 下一页. Generate a test for F using D algorithm for time frame 0. To test for A stuck at 1, we set input A to 0. This activated the for resulting in a value of D prime at the for side. Now we propagate this D prime through the AND gate. The other input must be a larger one. This requirement forces us to look backward. According to the algorithm, when values are recorded in D flip-flop, we must continue justification in the previous time frame. We call this time frame. This is where the 5 value logic fail in time frame. To justify a 1 at flip-flop input, the NOR gate in time frame must output 1. Consequently, inputs A in time frame must also be set to 0. However, the fault A stuck at 1 exists in every time frame, so setting A equal to 0 here actually produces a D prime again. The NOR gate input becomes D prime and 0 and not 1. In a good circuit, this output 1, but in the faulty circuit, its output 0. The result is D. This is conflict. We need a clean one to satisfy time frame 0, but the circuit gives us a D. Since D isn't equal to 1 in 5 value logic, the algorithm hits a conflict and fails. The next person.
Hey, I want to introduce 90 algorithm. First, just like a D algorithm, we start from time frame 0. We set an input to 0 because this can activate the fault. So the value at input becomes D prime. Next, we want the NOR gate to output D for fault propagation. To get D at the output of the NOR gate, we need the other input to be OU, 0U, because of the NOR gate property. If any input is 1, the output is definitely 0. So the other input can stay unknown and it will still work. Thus, at time frame 0, the pseudo primary output becomes D. Next, we pass the D to time frame 1. The goal in time frame 1 is to produce D at the final output. To do this, we must set the input to 1. After going through the AND gate, the output becomes D. Now we successfully observe D at the primary output. Finally, to the time frame -1, we look at the PPI of time frame 0, which becomes the PPO of time frame -1. This value must be 0U. So we need a NOR gate output to be 0 in the fault-free case. In the faulty case, it can be used, so we don't care. To make the NOR gate output 0, we just need one input equal 1. Therefore, we set the input of time frame -1 to 1. This gives us the correct PPO equal 0U. So the final test pattern is 101, and the 9-value algorithm is finished. Conclusion: the 5-value system cannot solve this sequential circuit. It only works completely for combinational circuit. For sequential circuit, 5-value logic cannot express all the required states. Only 9-value logic can correctly describe and solve sequential test generation. That's why.
And for question 3, to show why test generation could be hard for sequential circuit, we design a circuit as follows. The circuit is consists with exclusive OR gate, which is the key why the circuit is hard for us to generate a test. Next page, please. So first, we break the circuit into time frames, and as you can see, we can plot the D and Q on the circuit. And next page, please. As you can see in the first part of the circuit, to obtain the required input Q, it took 2 time frames for this circuit. This is the priority dependent, which is crucial to the test generation, and it is caused by the exclusive OR, which is a priority gate. Since this may happen whenever an exclusive OR gate is in the circuit, the more complex the circuit is, the more time frames we need to obtain the required input for our test generation. Okay, that's it.
And this flowchart shows the entire process of applying the 5-value decalculus to the full A star at 1, even after activating the fault, unrolling the circuit, and performing forward implication. The defunctor eventually collapsed because of the feedback path and unknown flip-flop state block propagation, and therefore no D or D block reach the output, and no test can be generated use the 5-value decalculus. And next page. And this is the flowchart for 9V algorithm. And use the 9V value logic can successfully generate a test for the fault A star at 1 by evaluating both a good and faulty value across multiple time frame. The 9-value implication is also preserve the fault effect and propagate to the output, where Z eventually become D or D prime. From this time frame result, we can extract the valid test sequence, demonstrating the 9-value logic success where 5-value logic is failed. And next page. And in this project, we first confirm the 5-value decalculus fail when feedback loop complete signal requirement make the A star at 1 for untestable. But by switching to 9-value logic, we resolve this and successfully derive the correct test sequence. For the difficult sequence test generation problem, we use an XOR flip-flop structure to illustrate how non-invertible gate complicate backtracing and make sequential test generation changing. And next page. And here is our contribution breakdown. And our leader is Li Yufan. And he doing the video presentation. And I'm the team member 2, Huang Xuanyi. I'm doing the flow chart. And the team member 3, Gao Yongjun, he doing the reflection report. And the 等一下，我的 and the Team member 4, Lin Junhan, doing the contribution sheet. And this is our project presentation. Thank you for everyone.